Welcome everyone to the very first online seminar of ESSI-BJ, our new seminar series called On Things to Come. I am Laura and I'm ESSI-BJ PR and Editorial Manager. And here you can also see Professor Wing-Wen Ip, who is the ESSI-BJ new Executive Director since last June. And thanks to him, we have now this new seminar series that actually is going to kick off today, but we have many other speakers lined up for the upcoming months. I would like to say a couple of words quickly about ESSI-BJ for those who are maybe new to our institution, and I hope you're not too many. But ESSI-BJ, the International Space Science Institute based in Beijing, was founded in 2013 thanks to the agreement between the International Space Science Institute in Bern and the National Space Science Center of the Chinese Academy of Sciences. And since 2013, we organize a wide range of activities that all aim to reach a deeper understanding of space science missions, the data yielded during space science missions, and we do it through a wide range of activities such as workshops, forums, international teams, or we also have visiting scientists coming to Beijing. And therefore, we mainly actually address the scientific community for our activities, and scientists, researchers, they can apply for any of these activities at any time during the year. Only international teams, there are small groups of researchers and scientists actually should apply through our annual call that is released every January, and it's a joint call with the International Space Science Institute in Bern. Our focus is on multidisciplinary and interdisciplinary research. We cover a wide range of areas of space science studies. And as mentioned, since June 2020, we have a new executive director, Professor Ip, who is unfortunately now still in Taiwan because of the current situation, the current circumstances, but we hope he will be able to come to Beijing very soon, and we hope we will be able also to host face-to-face, in-person meetings very, very soon. In case you have any questions or about ESSI-BJ, you can always contact me. I will leave my email in the chat tab below, or you can also visit our website. I have already copied it in the chat tab below. And now we will defer to Professor Ip to say a couple of words about our very first speaker, Professor Jones. Thank you.
Yes, thank you. And hello, everybody, and welcome to this webinar, the first time we have for this On Things to Come seminar series. And the first one will be given by Professor Geraint Jones of the University College London. He is the head of the Planetary science group there. And Professor Jones, he got his PhD from UCL's Mullard Space Science Lab. And then after his PhD, he also worked at the Imperial College London, and NASA Jet Propulsion Lab, and also at the Max Planck Institute for Solar System Research, before returning to Mullard in 2007. And his scientific research field is mainly focused on the solar wind and the interaction with the small bodies, and also on the giant planets' magnetosphere and their moons and rings. And he has a wide range, of participation in spacecraft mission for planetary exploration. And for instance, he was involved, and he's still a member of several important major missions, including Ulysses, Cassini-Huygens, the Solar Orbiter, ExoMars, and the JUICE mission, which will be going to Jupiter soon. And now, for this present seminar, he was the main proposer, the primary proposer for this proposed mission called Comet Interceptor, which is the topic of today's seminar. And as a consequence, he's now the principal investigator of this very important mission, which I think, as Professor Geraint Jones would tell us, that will consist of 3 spacecraft. I think 2 from ESA, right, and 1 from Japan, JAXA. So we will be hearing from Professor Jones in the next hour or so on this very exciting development. Geraint, it's all yours now.
Okay, great. Thanks very much. Thank you to Laura and to Professor Ip for the very warm welcome. So I'm very grateful for this invitation to give this talk, and honoured to be the first one giving a seminar on things to come. So, so during the next hour or so, I'll give an overview of the mission, Comet Interceptor, to you, as shown here in the title, an ESA mission to an ancient world. But as was just mentioned, there's also a major contribution to the mission from our colleagues in Japan as well through JAXA. I'm the mission PI for Comet Interceptor, but the deputy PI is Colin Snodgrass, who also plays a very large role in running the scientific side of the mission, and we're supported by a team which is now about 250 people in many countries. So first of all, this is where I work when I can get to my office. So this is the Mullard Space Science Laboratory. So it was set up in the late 1960s by University College London, and with the largest space science group in the UK at a university. So we have 200 people on site, so engineers designing and building instruments, also academic staff, postdocs, and PhD students as well. So the background of this photo I took in 1997 is Comet Halley. So a uniquely large comet, which I'm sure many of you online will remember seeing back then. So Comet Interceptor, obviously, as the name suggests, is a mission to a comet. So here's a photo over Germany in July of Comet Neowise, which graced our skies for a few weeks back then, a very beautiful sight. And I'm sure most of you online listening to this will be aware that comets are icy bodies, most of which are orbiting well away from the sun in the frozen depths of the outer solar system. And it's only when they venture close to the sun that the ices on the surface sublimate, releasing gases and carrying dust out into space as well. So the gases become ionized, forming an ion tail, which you can just about see in this photo very faintly. And then you also have a dust tail as well. So the dust grains are so small that they're affected by radiation pressure. So they follow a slightly different trajectory to the nucleus, trailing behind it and forming a dust tail. And obviously from learning about these bodies, we can learn a lot about the conditions in the solar system billions of years ago when the planets were formed. It's believed that many of these bodies were thrown out of the solar system early on through close interactions. So if we can see one of these bodies close up on its first approach to the sun, we're basically seeing one of these frozen building blocks from the formation of the solar system. And the more we understand about them, the more we know about the conditions that were present when the planets were formed. So obviously this is not by far the first Comet's mission. The most well-known periodic comet is Comet Halley, which returns to the inner solar system every 76 years or so. And for the mid-1980s return of Comet Halley, there was a huge effort by several countries and international organizations to get missions to this comet. And Giotto, shown here, was the European Space Agency's first interplanetary mission, and it was targeted to approach close to the nucleus of Comet Halley in March 1986. So in September 1985, NASA had performed a flight through a tail of a comet, Giacobini Zinner. That spacecraft didn't carry cameras, but it did return valuable data on how a comet interacts with the solar wind. And then a few months later, Giotto and spacecraft from the Soviet Union and Japan encountered Comet Halley as well over a couple of weeks as it crossed the ecliptic plane. So Giotto was a spin stabilized spacecraft, so it was rotating around the vertical axis shown here. It had a dust shield. Because Halley orbits the sun in a retrograde direction, so opposite to the direction in which the planets orbit the sun, the flyby speed was incredibly high, so 76 kilometers per second, which meant that 68 kilometers per second, which meant that dust particles hitting the spacecraft with that velocity, even tiny ones, can cause a huge amount of damage. So this dust shield was included to protect the spacecraft, which was moving in the downwards direction as it went through Comet Halley. And the spacecraft did indeed survive, returning amazing images and data from in situ instruments as well as it traversed the coma of Comet Halley. It didn't go through without incurring some damage, however. So the Halley multicolor camera you see here, its baffle was damaged, and so there are no images returned from after closest approach. But enough of the spacecraft and instruments survived for it to go on to another comet encounter in 1992 when it encountered Comet Grigg-Skellerup. So here you can see an engineer working on one of the instruments, and to give a sense of scale for the spacecraft, and also the launch on an Ariane rocket in 1985. So this sequence of images from the Halley multicolor camera led by Uwe Keller shows the nucleus of Comet Halley, obviously sped up. But one of the big surprises from this mission was that comet nuclei are incredibly dark. So they're as dark as coal, reflecting very small amounts of sunlight. So the camera was targeting the brightest point in the scene, which in this case was a jet of material, and the sun is off to the left. So there have been several other missions, of course, Deep Impact, Stardust, etc., from NASA, but it is the Rosetta mission which studied Comet Churyumov-Gerasimenko for a few years earlier this decade, where we've learned the most about one particular object. So this sequence of images returned from the Rosetta spacecraft show jets of material coming off the nucleus, and Rosetta, instead of just flying past the comet, spent a long time after its launch in 2004 to reach a comet, to match orbit with it, to travel alongside it. So as this comet neared the sun, Rosetta watched it become more and more active. You can see the jets there as the nucleus rotated. So there was a wealth of data returned from Rosetta and its instruments, and we've learned a huge amount of this about this particular comet and its composition. There was also a lander as well, Philae, and it was dropped to the surface in November 2014, and you can see on the surface of the comet there, Philae, which was its final resting spot, was discovered by Cecilia Tubiana, looking through images from the last couple of weeks of the mission, resting on the surface. So the landing was incredibly challenging with this extremely low gravity environment. So when it touched down, it bounced off and eventually came to rest next to a cliff face. So just before the end of the Rosetta mission itself, it revealed the position of Philae on the surface. So this mission showed us a lot about one particular comet, and the Rosetta mission has been incredibly successful in doing that. But just to put the observations into context, here are images returned from several different spacecraft missions to comets or comet nuclei. So you can see 67P here, the Rosetta target comet, the nucleus measuring about 4 by 3 kilometers, and then we can see other nuclei encountered by NASA spacecraft, so Hartley 2, Temple, Borelli, and Wild 2. And then here is an image of Halley, this time an image taken by one of the Soviet spacecraft Vega 2, and you can see that the Halley is the largest nucleus we've encountered so far. And then the new New Horizons spacecraft that was sent by NASA to conduct the first flyby of Pluto encountered a body in the Kuiper belt named Arrokoth, which is shown here on the left. You can see it's a much larger body. It's unlikely that this body will come in towards the sun in the future to become a comet, but it's a good example of the type of object which is believed to be the source of short period comets. So we have from many different missions data on several different objects, but by definition all these missions have gone to comets which are in orbits that carry them around the sun over relatively short periods. We have not yet encountered a comet that is coming in towards the sun for the very first time. So that is what Comet Interceptor plans to do. So it's a mission targeting a long period comet, preferably dynamically new, which means that it's coming in towards the sun for the first time since the body was formed. Or if we're very lucky, we could even get to an interstellar object, which is just passing through the solar system. So why do we want to do this? So as I've just said, previous comet missions have been to objects that have passed the sun many times. So we believe that every time a nucleus passes relatively close to the sun, the surface ice is melted, they sublimate, and carry dust away. So when we encounter a comet, a short period comet with a spacecraft, we're not seeing it as it was when it was formed. The surface layers have been eaten away. The surface morphology has been sculpted by the heat from the sun. So we're not seeing a truly pristine object, or not seeing the outer layers of a truly pristine object. I showed the images from Giotto showing how dark Comet Halley's nucleus is, and it's believed to be this dark because there's a thick layer of dust. So every time the nucleus passes perihelion, is heated, a lot of dust is thrown out into space, but the dust that does not reach escape velocity actually falls back down onto the surface. So it may be the case that that new comets are actually quite icy on the surface and bright and reflective, but that the comets we've encountered, because they've been past the sun many times, are much darker than they were originally because they've been coated in a thick layer of dust. It may be the case that if we see one of these objects coming in towards the sun for the first time, we'll be able to see a surface that has not been darkened by a coating of dust, and we'll be able to have a direct view of the surface ices. So yes, we want to target a pristine comet, so a mission that complements the data returned from previous comet missions. So the reason that we've only gone to periodic comets in the past, short period comets, is that we need to know where the comet is in the future, and you can only do that if you know the comet's trajectory, what its orbit is. And obviously comets like Halley and 67P are in orbits that are very well known, and they can be studied from Earth over a large portion of their orbit to refine our knowledge of where they're going to be. So it's going to be much more challenging for Comet Interceptor, because we want to go to an object where we don't know its trajectory beforehand. We don't know when and where it's going to cross the ecliptic plane where we can reach it with a spacecraft from Earth. But ground-based observatories are improving in their capabilities quite dramatically. So we are now able to find comets much earlier as they're coming in towards the sun for the first time, and we're anticipating a revolution in the distances at which comets are discovered through the Vera Rubin Observatory, so which is formerly known as LSST. So the Rubin Observatory will be carrying out a survey of the entire sky every few nights once it starts operations in a couple of years' time in Chile. So with this facility, we know that in only a couple of years, we'll have the ability to find comets much further away from the sun, and we'll be able to calculate their orbits earlier, and we'll know where they're going to be with enough time to send a spacecraft to them. So even with this capability, if we have Vera Rubin Observatory finding comets at great distances, that's still extremely challenging to build and launch a spacecraft to travel to a comet. So we need some additional shortening in the lead time of in sending a spacecraft to a comet as well. And the solution to that is that we send a spacecraft into space ready to encounter a comet that's nearing the sun for the first time. So if we can design a spacecraft that can encounter comets with a wide range of trajectories, then we can build and launch it and let it wait in space. At the same time, observatories on the Earth are looking for suitable targets or suitable targets for the mission. And then once we know the targets, we work out how to get there, when to leave. And so we'd expect once a suitable target has been found that we'd leave a location near the Earth to within 6 to 12 months to of the discovery of the target. So Comet Interceptor is going to be waiting in space at L2. So it's one of the Lagrange points, and L2, or Sun-Earth L2, is about 1.5 million kilometers further away from the sun than the Earth is. So shown here, the little cross here on the far side of the Earth, seen from the sun. So spacecraft placed there are in a relatively stable position. So with some station keeping operations every 2 or 3 weeks, a spacecraft can stay there for years. And previous missions such as Herschel, Gaia, and Planck have already been operating in that location. So 2 years ago, ESA issued a call for mission proposals, and it was for a new type of mission which has been called F-class by ESA, and it was for a mission to launch with the Ariel exoplanet observatory on an Ariane 6 rocket, and Ariel will be launched to L2. So this is a perfect opportunity to send a spacecraft to L2 and where we can wait for a suitable comet to come along and then leave it with relatively small amounts of fuel to encounter a comet. So the constraints on the mission are that the maximum cost to ESA at the end of the mission are 150 million euros. The launch is not included in that cost. It's a launch with Ariel on an Ariane 6 rocket. So you can see Ariane 6-2 rocket here on the right, the type of which we'll be using for this mission. And as is usual, ESA member states and other collaborating agencies fund the instruments and the science teams. So the launch is planned for 2028, and the 2 spacecraft will launch together towards L2. So once we arrive at L2, Ariel will start its mission of studying exoplanets around other stars, and Comet Interceptor will begin its wait for a suitable target comet to be discovered. So designing the spacecraft and the mission is not straightforward, however. We may encounter comets, as was the case for Halley, that are orbiting around the sun in a retrograde direction. So if the comet is coming around the sun in the opposite direction in which the Earth is going around, then our closing speed can be greater than 70 kilometers per second. Also, we can't predict our path through the comet. So in the case of Halley, Giotto was designed specifically for an encounter with Comet Halley. So the dust shield was facing the direction of travel. The high gain antenna was tilted exactly to point towards the Earth on March the 13th, 1986. So when Giotto went to a second comet, because the geometry of that flyby was different, it actually had to go through the comet slightly sideways to maintain communications with the Earth. But we have to design a spacecraft that can go through a wide range of different comets, different observing or fly past geometries. And the cost limit means that the entire mission should be shorter than 5 years in duration. Obviously, building a spacecraft and its instruments is expensive, but also operating spacecraft, as many of you listening will be aware, it's also an extremely expensive endeavor as well. So the longer the mission goes, the more the cost increases. So there's a limit to the duration of the entire mission. So we can't wait at L2 for an infinite amount of time until the perfect target comes along. We'll have a limited time in which to leave L2. So the solutions to this are we have a limited radio link to the Earth at the encounter, so we're not going to be streaming all the high resolution data in real time as we go through. And we're going to build the spacecraft with dust shielding equivalent to that used on Giotto. So Giotto survived an encounter to within a few hundred kilometers of the nucleus of Comet Halley. So we know that dust shield design worked well there at those high speeds, and we need similar shielding for Comet Interceptor. The way to L2 is probably going to be limited to around 3 years, and if we haven't found a suitable comet target either before launch or during the first 3 years after launch of the mission, then we'll send the spacecraft to a short period comet target instead. But the instruments being carried on Comet Interceptor, as I'll describe in a moment, are some of them are quite new and haven't been used at a comet previously. So if we do go to one of these backup targets, then it would be new science as well. It's not a repeat of previous missions. And then finally, just to point out that the mission has to be a flyby. We can't do the same as Rosetta, match orbit with a comet and spend weeks or months traveling alongside it. It is the type of mission like Giotto, Vega, Sakigake, and Suisei at Halley, which were flypasts. So we go past at high speed. The range of flyby speeds is between 10 kilometers per second and around 70 kilometers per second. We have to design the mission to be able to gather all the key data within the space of a few hours when we're closest to the comet. So this just gives an overview again of, to recap what I've just said, how the mission will operate. We'll launch from the Earth in 2028, is the Earth and its orbit around the Sun, and we'll go to L2, where we'll be put in an orbit that keeps it around the L2 position. And then we wait for up to 2 to 3 years for a suitable target comet, a new comet coming in towards the Sun, to be found. So during that time, if we haven't found a comet before launch, then observatories on the ground will be used to find new potential targets. And the plan is that we discover a target that we can get to from a ground-based observatory. So during this time, Comet Interceptor will not be operating. It'll be in hibernation and just kept in a position around L2. It will not be searching for the target comet itself. So for each potential target, the trajectory is calculated, and there are restrictions to where we can reach with the spacecraft. So we can't go a very large distance inwards from the Earth's orbit because of thermal reasons, and similarly, we can't go very far from the Sun either. So the range of distances over which the mission can operate will be defined in the near future, but it's going to be a band centered on 1 AU. And also we can only encounter comets when they cross the ecliptic plane, so when they cross the plane of the Earth's orbit around the Sun. So for each comet, it'll cross the ecliptic plane at one location, but for a few comets we might be able to get to 2 locations when the orbit reaches perihelion to the south or the north of the Sun and crosses the ecliptic plane twice, close to 1 AU. We may have a choice in that case. But for each comet discovered, we can only get to them if they're within a certain distance range from the Sun when they cross the ecliptic plane. So when a suitable comet has been found, at the right time, the spacecraft is directed to leave L2 and is put on an interplanetary trajectory to encounter the comet when it's crossing the ecliptic plane. And as the comet gets closer to the Sun, the nucleus gets more active, the ices start to sublimate, it grows a gas tail, an iron tail, and a dust tail. So when the spacecraft reaches that comet and encounters it, the comet will be much more active than it was when it was discovered many months or even a couple of years before the date of the encounter. So during this fly past, as I said, that's when all the key data will be gathered by the spacecraft's instruments. So just to give an example of that, there have been comets that we could have reached if we had a mission like Comet Interceptor already in space at that time. So Comet 2001 Q4 that was found by the NEAT survey was found 3 years before it reached perihelion. If the Vera Rubin Observatory had been operating then, it would have found it around 8 years before perihelion, so giving a very long lead time. And in this case, the target would have been known before the mission was launched. After reaching L2, the spacecraft would wait there for about 1.5 years, and then it would take about 3 years to get to the point where it would encounter the comet. And as I mentioned briefly earlier on, there's a really exciting possibility as well that we could encounter an interstellar target. So it's only in the last couple of years that we found confirmed interstellar objects, and Oumuamua, the long object shown here in the ARTIS impression, was the first one. And then that was barely active, so not really a comet, but there are signs that it was outgassing. And then that was followed by Comet Borisov, found by an amateur observer. So having found 2 interstellar objects like this just passing briefly through the solar system, there's a possibility the Comet Interceptor could get to one of these objects if one is found in the right time period. As I said, crosses the ecliptic within a certain range of distances, and obviously is found with enough notice. So we are planning to go to a long period comet, but if an interstellar object is found, then we could potentially get to one of those as well, which is very exciting possibility. So I'll just take a brief moment to address a couple of questions that have been posted. So yeah, one question: would an interstellar comet be as primitive as a comet of our solar system? Yeah, it depends on the history of that object. We honestly don't know, and these objects, many of them may have been ejected from their stellar systems when the system was being formed, but also could have been ejected well after the formation of that stellar planetary system. So I guess there will be a range of possibilities for the life history of these objects. We honestly don't know. And then why L2 rather than L1 for the waiting point in space? Well, that's a constraint due to the ESA call, because the mission call was specifically for a spacecraft to launch with the Ariel mission, and Ariel is, it's already decided that Ariel is going to L2, then Comet Interceptor will also be going to L2. So I'll address other questions later on. So what are the science goals of the mission? Obviously, we want to see the nucleus of our target in great detail, understand its surface morphology, and ideally also its composition and thermal signature. We also want to look at the neutral coma, so the nucleus is giving off gas, study the jets of material coming off the nucleus. The jets are not as well collimated as dust jets, but they still give an indication of the distribution of gas that's escaping from the nucleus. And also to look at the dust itself as well. So there are dust jets. These are examples of images taken from the ground, and from looking at the jets on approach, we can already tie down things like the rotation period of the nucleus if it hasn't been determined from the ground, and also from the rotation of the nucleus, we also get curving jets as well, as shown in this other example from a ground-based image. So we'll be able to see these features over a range of distances from the comet. We're also going to look at the plasma as well. So all comets are embedded in the solar wind. So the neutral gas that's released from the comet becomes ionized primarily by solar radiation, but also things like electron impact ionization. So the comet is also surrounded by an ionized medium. These pickup ions, these fresh ions from cometary gas, join the flow of the solar wind. So there'll be in situ instruments to measure the characteristics of the plasma, but also remote sensing instruments as well. So there's one instrument, which I'll mention in a few minutes, that's going to map the ion tail over large distances, and also we'll see if we can image ion structures close to the nucleus as well, or in the coma around the comet's head. So we'll have a mixture of in situ observations from plasma instruments and also remote observations of the plasma as well, which is the first time that this will have been done on a cometary mission. So on the upper right here, this is an image of Comet Hyakutake in 1996 from the UK Schmidt telescope. So the dust tail, the main dust tail is here, and the grains along the comet's orbit, and here we can see the ion tail. So it would be fantastic if we're able to see these structures in both tails, both from the spacecraft and from ground-based observatories at the same time. So as Professor Ip mentioned earlier on, this is a multi-spacecraft mission. So it's an ESA-led mission. JAXA is making an extremely valuable and major contribution to the mission by providing one of the 3 spacecraft and the instruments that it'll be carrying as well. So the instruments, the spacecraft comprise of the main spacecraft, which for now we're calling Spacecraft A. So this will be the one that is communicating with the Earth and carries arguably some of the key instruments for imaging the nucleus and the mass spectrometer as well for sampling the composition of the coma. So this spacecraft will be targeted probably at a distance of around 1,000 kilometers of closest approach. So it will carry a dust shield, but it'll be at a distance which is considered safe for the survival of the spacecraft. And then there'll be 2 smaller spacecraft, one provided by JAXA and institutions in Japan providing the instruments for that spacecraft, which for now we're calling Spacecraft B1, and an ESA spacecraft, a spin-stabilized spacecraft called B2, which will also venture closer to the nucleus. So the flyby distances for these 2 spacecraft are under discussion, but obviously they're going to get much closer to the nucleus than the main spacecraft. So we're looking at flyby distances of a couple of 100 kilometers for these 2 smaller spacecraft. So it's known already that these will be passing through a more dangerous part of the comet, especially if it's a very high speed encounter. So we live with the risk that we may lose either or both of the spacecraft, but the value of the data returned by these will balance out that risk. So this cartoon gives an overview of what the encounter will be like. So of the order of 1 day to 2 days before closest approach, the main spacecraft will release the 2 small spacecraft, B1 and B2, and they'll travel more or less in parallel past the target. And during the encounter, the 2 small spacecraft will send their data streaming to spacecraft A, which will record the data from those 2 spacecraft on board. So they'll all be traveling in parallel past the nucleus. So the 2 small spacecraft will get closer to the nucleus, but as I just said, we may be lost due to dust impacts. But as the data is being streamed in real time to spacecraft A, the data will be safely on board. There will be some communications with the Earth during the encounter, but not a great deal of data. Most of the data will be sent back from spacecraft A after the closest approach to the comet. And we may have a short period where if the 2 smaller spacecraft survive, then we get additional data after the encounter. So I'll briefly run through the payload. I won't go into great detail with these, but just to outline the scientific instruments that will be carried. So these are the spacecraft instruments on spacecraft A, the main spacecraft. So led by Nick Thomas from the University of Bern is COCA, the Comet camera, which is going to return the highest resolution images of the nucleus, or it's expected to. And it's based on the CASIS camera, which is on the ExoMars Trace Gas Orbiter. Also led from the University of Bern by Martin Rubin is the MANIAC mass spectrometer, which benefits from heritage from Rosetta. Led from the University of Oxford by Neil Bowles with KOPI in Finland is MIRMIS, which is an infrared camera, so we'll get thermal observations of a nucleus for the first time. And then there's the dust field and plasma package led by Hanna Rothkiel from Warsaw in Poland, but that will comprise of many different sensors from many different countries that will sample or detect dust impacts on the spacecraft, the characteristics of those dust, and the plasma environment around the comet as well. Our colleagues in Japan will be providing for spacecraft B1 a hydrogen imager, so a far ultraviolet camera, which will map the comet in Lyman alpha. So they have a strong heritage for that type of instrument from the Procyon small spacecraft. A plasma suite will comprise a magnetometer and an ion mass spectrometer. And there'll also be 2 visible light cameras as well, a wide angle camera and a narrow angle camera, which will get images of the nucleus around closest approach to complement those of COCA on spacecraft A. And then spacecraft B2, which is the ESA small spacecraft, will include ENVIS, which will map the entire sky almost around the spacecraft, looking at ions, dust, and neutral gas. OPIC, led from Estonia, is a camera that's going to be looking in the direction of travel of B2. So it has a periscope design, so the main camera will be behind a dust shield, and you can see an early model of this camera on the right. And then 2 sensors from the dust field and plasma package, dust impact sensor again, and a magnetometer from Imperial College. So the ESA team have already, as part of the evaluation of the mission, carried out a concurrent design facility study of the mission, and this is the concept for the mission. So it's main spacecraft A with solar panels, and the 2 small spacecraft B1 from Japan with fold-out solar panels, and the spin-stabilized spacecraft B2 shown at the upper left. So I stress that this will not be the final design. So this was a concept put together by ESA and industry will be refining or are putting forward their designs for the spacecraft as well. And in a matter of a few weeks, we'll know what those who are bidding to build the 2 ESA spacecraft will be proposing. So in the interest of time, I'll move on and just describe what the encounter will be like. So spacecraft A, shown here in yellow, will get images of the nucleus at high resolution, so up to 8 meters per pixel is the target for closest approach. And the other spacecraft will also get images of the nucleus. So from getting multiple viewpoints of the nucleus, it'll help constrain the shape of the nucleus, the direction of the dust jets in 3 dimensions. So there's a benefit to carrying out multi-spacecraft observations like this. Also, the dust, so the plasma instruments will carry out multi-point observations as well, which will help us build up a 3D picture of the interaction of the comet with the solar wind, rather than only getting measurements along one trajectory. So I'll briefly return to one of the instruments which I'm actually leading, called ENVIS, which stands for Entire Visible Sky. It'll be on spacecraft B2, and that instrument will use the spacecraft's rotation to sweep across the sky, mapping almost the entire sky as seen from spacecraft B2. So rather than just concentrating on the nucleus, we'll be able to look at the large-scale structure of the coma surrounding the spacecraft as well. And from those observations, then we may be able to construct a view of the comets over extremely wide field of view. So you might be able to put on a virtual reality headset and view the comets as it was seen by the spacecraft as it went past. So progress with the mission. So the initial selection of the mission for study was in June last year, and then in July and November, ESA carried out detailed studies of the mission, and they concluded that the mission design was indeed feasible, that what we proposed can be done and within the financial budgets. So it was in February of this year that ESA approved that the mission moves on from phase 0 to A, and so that was the formal selection of the mission for ESA's F-class program. So ESA issued an invitation for industry to propose to build the spacecraft in May, and those bids were submitted in July. So that review of the industrial contracts is underway, and we should hear in the next few weeks which 2 industrial teams have been selected for further study of the mission, and then in around 2 years' time, ESA will formally approve the mission, and one of those 2 industrial teams will be selected to build the 2 ESA spacecraft. So right now there's a full instrument review being undertaken by ESA, so it's an incredibly busy time for the instrument teams. So shown here are many working on the concurrent design facility study late last year, and the photo lower right is Colin Snodgrass, the deputy mission PI, and Chechi Tubiana, who's on the science team, the operations coordinator for the science consortium. So I work closely with the both of them on coordinating the science team side of the mission. So somewhere out beyond the orbit of Pluto, there is an object which is gradually making its way in towards the inner solar system, and it will be the target, we hope, of Comet Interceptor. We don't know where it is, where it's going, and when exactly we'll encounter it yet, but if all goes to plan, we'll have a spacecraft to encounter it in roughly a decade's time. So here's the mission team. Last time we were able to meet face to face, which was in December of last year. So we've got an incredibly busy team and really excited with the scientific potential of this mission. And if anybody wants to find out about more about the mission, then the website is shown there at the lower left. So I'll leave it there. Thank you very much for your attention. So,
thank you very much. Oh, sorry.
No, it's fine.
Thank you very much, Professor Jones, for your lecture.
Thank
so
you.
we have questions, right, Geraint? If you care
Yes.
to answer some of them.
We have actually a couple of questions. I will immediately share them also in the chat so that everyone can see them. But I think that now Professor Jones can already see the questions. The first one is from Professor Blanc.
Mm-hmm.
I don't know if you, Professor, you can already see it, correct?
Yes, thank you.
Perfect.
So I'll read it out. Good to hear from you, Michelle. So do you have an estimate of the probability that we'll fly to a new comet as planned rather than having to fly to a backup, given that we have a 3-year wait time at L2? So we believe that we have a very good chance of doing this. So off the top of my head, it's roughly 70% chance we believe. So one way we've approached this is to look back in time. So earlier I gave an example of a comet. Had that been coming past in the near future when Comet Interceptor is in space rather than in 2001, would be able to reach it. So we've looked at all the comets that we could potentially have reached, and also folded in the capabilities of the Vera Rubin Observatory, also other survey telescopes which are looking at the northern hemisphere, including Pan-STARRS, etc. And we believe that we have a very good chance of finding a suitable comet. So it's around 70%, but a formal study is awaiting publication. So that's just an approximate number. So the backup targets, many of them are very scientifically interesting. So another question that Professor Ip posted during the talk was about which of the backup targets is the most promising. And I think 73P, which is a comet that broke up in the mid-1990s, is particularly interesting because even though that's a comet that's come past the sun many times, because it broke up in the recent past, if we encounter one of its nucleus fragments, then we would be seeing the inside of a recently broken nucleus. So yes, there's a question again about why we're going to L2 rather than L1. So that's because of the constraints of the call for the mission proposal. Because we're launching with the Ariel mission, that is going to L2, and that will not be changed. And so Comet Interceptor will also go to L2 as well.
And I think Professor Heap has sent several questions in the chat.
Yes, so I see, one unanswered question is, would we consider hitting the comets with one of the spacecraft? So the targeting of all 3 spacecraft will be more challenging than it has been for previous missions. So because we're finding a comet on its first pass through the inner solar system, the orbital path won't be as well known as is the case for short period comets, so all the comets we've visited previously. So there is an increased uncertainty in the flyby distances. So there is a non-zero chance that one of the 2 small spacecraft could potentially hit the nucleus. So we may find that even if we target, say, 500 kilometers from closest approach, if the uncertainty in the nucleus position in what's called the B plane, where we pass closest to the comets, we may have the nucleus in that uncertainty envelope. So there is a chance that we may hit the comet inadvertently. It wouldn't be done by design, but as I said, the 2 small spacecraft, we're considering them, although obviously we hope that they would survive the encounter. We are very aware that we could lose them at any moment going through the most dangerous region immediately surrounding the nucleus. So we would take the risk of hitting the nucleus with the same together with the risk of being hit by a large dust particle and bringing the operation to an end. If we do hit the nucleus, then obviously, as was the case for deep impact, we would form a crater which would be imaged by the camera on spacecraft A, and also by the other small spacecraft as well. So there would obviously be a scientific benefit to that as well, but we're not planning for an impact.
Okay. I see there are no other questions for the other attendees. If you want to submit a question, you can do it through the question tab. I haven't received any so far. Professor Eep, if you have any other question for Professor Jones.
I think I have made enough questions, but we will continue, we'll continue. Maybe very soon we'll have Professor Jones come back to give another talk. As mission plan moves ahead. So I think that it's almost time now, and I want to thank Professor Jones, for giving such an excellent and interesting talk and to kick off this seminar series. And then and I think that the next one will be 2 weeks from now. And then it's about is it about Dragonfly? Is the next mission to Titan? So I hope that everybody would turn in at that time. And thank you, everybody.
1 second. I'm sorry. There is actually one last question by Professor Liu. Exactly.
Yes, okay, so I can see the question. So yeah, is there anything worth observing during the long waiting time? Well, the science team definitely would say yes. We have some very capable instruments on board, and we would love to carry out observations during the wait time or during the cruise. There will be a short opportunity when we commission the instruments when they're first switched on, but the plan is, because of the limited costs of funds available for operations, that almost all the observations will be just for the target comet. So everything we're planning for is just for the operations near the comet itself. Once we're in space, then obviously it would be great to make observations, but not currently planned to observe anything during the wait or cruise. Thanks for the question.
Thank you. So, Laura, so we conclude this seminar at this point in time?
Yes, I think if there are no further questions, which seems to be the case, thank you very much, Professor Jones.
Thank you very much. It was a pleasure to give this talk, and many thanks for the attention of all the attendees.
Yeah,
thank you very much.
Hope to see you at the ISSI-BJ next time.
I hope so. Yes, it'd be good to meet people in person again.
Okay, very good. Thank you
also,
again.
yes, to Professor Blanc, who actually congratulated Professor Jones on the great talk. And yes, a quick reminder, we have our next seminar on October 21st by Professor Ralph Lorenz on the Dragonfly mission, and then Professor Wang Chi on the SMILE mission on November the 4th, and then Professor Heike Rauer on November 25th. But if you have signed up to our newsletter, you will receive an email very, very soon. Thank you very much once again.
Thank you, everyone. Goodbye.
Bye-bye.